Okay, let's say we have an exponential PDF. Our PDF is in the form of 1 over lambda e to the negative x over lambda, where our support is for all positive values x. Let's verify that this actually is a PDF, and to do that, we will integrate over the support from 0 to infinity, and we want the whole area under the curve to equal 1. Okay, let's think about what the graph actually looks like. Ignoring the parameter lambda, 1 over lambda, we will look at the graph of e to the x. We saw that our graph e to the x kind of looks like that. This is e to the x, this is e to the negative x, and this is negative e to the negative x. Okay, why did I do that? Because to integrate this function, we have to think about what happens when we derive it. X over lambda. What happens when we derive it? Then we end up with the chain rule, and so we have the derivative of the outside is just itself, so e to the negative x over lambda times the derivative of the inside, and that'll be negative 1 over lambda. And so if we integrate both sides, then we see that on this side, this is exactly what we have up here, right? These two are the same. And so I can use the fundamental theorem of calculus to kind of get rid of this integral and the derivative. So I'm going to erase this. Okay, and I'm going to add a negative sign here. And that's how we integrate. Okay, so because we're going from 0 to infinity, we have to use the fundamental theorem of calculus and plug in our values 0 and infinity. Okay, notice that this side of the equal sign, we have our function being negative e to the negative x over lambda, and we can base our intuition off of this graph right here, so this one. Okay, so what happens when we plug in infinity? Well, we get 0. Why? Because it approaches 0. More formally, we'll have limit as x approaches infinity of negative e to the negative x being equal to 0. And we see that this is clear because exponentiation to the negative e to the negative x is equal to 1 over e to the x. And so as x becomes larger and larger, then the whole graph becomes smaller and smaller. And it approaches 0. Okay, what happens when we plug in 0? Then if we plug in 0, we'll get negative e to the negative 0, which is just negative e to the 0. But anything to the 0th power, as long as it's non-zero, would be 1. So we'll have negative 1. And so because we're going from, remember our limits were infinity on top and then 0 on the bottom, then we have to do the function e to the negative e to the negative x over lambda. Plug in infinity, we got 0. Plug in 0, we got negative 1. And so we have 0 minus negative 1. And so we get 1. And so this shows that we have a PDF. Okay, now let's calculate the mean and the variance. Okay, mean and the variance. Okay, let's calculate the mean. By definition, expectation x, is given by the integral over the support x times fx dx, where fx is the PDF. And so plugging in the PDF, we get x times 1 over lambda e to the negative x over lambda dx. Okay? And so we just have to integrate this, but then we're going to use integration by parts. So on this side, we have a polynomial being multiplied to an exponential function. So remember that exponential functions are easier to integrate than polynomials, okay? And so remember that if we have two functions, one of them's easier to integrate, then we pretend like it was a derivative of another function, and integration by parts shows us that this is equal to the integral of that function f minus the integral of f g prime. So we derive g and we integrate f. So here g was not derived, but here g was derived. Okay, let's plug that into our formula. And so letting g be x over lambda, and then f prime being e to the negative x over lambda. Let's think about what f is. Okay, g is easier, so let's start with the g. The derivative of g is g prime is 1 over lambda. Okay, and when we integrate f, then we'll get e to the negative x over lambda and negative 1 over lambda. I did that in my head, but then you can check by using the chain rule that indeed if we derive our function, we'll end up here. Actually, I did it wrong, so it's bad to do it in your head. It'll be negative lambda. Okay, let's try deriving it just to make sure. When we derive it, we use the chain rule, and so the outside remains the same, and so we have the outside here, and then the inside derives, and so if we derive the inside function, then we'll get negative 1 over lambda, which cancels with this guy, and so we end up with our function f prime. Okay, so let me erase that. Okay, and so plugging it into the formula, we get f times g, which is negative lambda over lambda, x e to the negative x over lambda, minus integral of f g prime. G prime is 1 over lambda, and so we'll have negative lambda over lambda e to the negative x over lambda. Remember, we're going from 0 to infinity, and so here we can calculate our values from 0 to infinity. And when we do that, let's do the left side first. Notice that when we plug in infinity, then we have the limit. The lambdas cancel out, but we'll see that it doesn't matter because we'll have the limit as our function x over e to the x over lambda, approaching with x approaching infinity. This will be 0 because e grows so much faster than x. Formally, we can use L'Hopital's rule, and because the top and the bottom both go to infinity, we can derive both, and we'll get this being equal to 1 over e to the x over lambda, 1 over lambda. And so only the denominator is growing, and we get 0. Okay, and when we plug in 0, we'll get 0 times e to the 0, which is 0 times 1, just 0. And so this whole left side cancels out to 0. Okay, and let me cancel the, let's look at the right side. Let me cancel the negatives, and let's cancel the lambdas. And we just have a simple integral, right? From 0 to infinity, e to the negative x over lambda dx. And when we actually integrate it, let's do it on our head, but we're using the chain rule backwards. And so we'll get x over lambda and then negative lambda, right? From 0 to infinity. Okay, again, when we plug in infinity into the x, we have 0 because it's as if we're plugging in infinity in here, right? And then as the denominator grows to infinity, then it becomes 0. So let me erase that because it wasn't formal mathematical notation. And so it's 0 minus, and then let's plug in 0. Okay, so we'll have negative lambda e to the 0. And so what's e to the 0? It's 1. The negatives cancel, and we end up with lambda. So expectation is lambda. Okay, let's think about variance. To do variance, we're going to use the formula that variance of any random variable x is equal to the second moment minus the first moment squared. And this is because of the definition of variance. Remember that the definition of variance is expectation of x minus mu x squared. And then if we just FOIL the inside, then we get x squared minus 2x mu x plus mu x squared. And because mu x is a non-random variable, it goes outside of the expectation. Using linearity, we get expectation of x squared minus 2 mu x, and then expectation x is equal to mu x, right? Okay, plus mu x squared. And because we have negative 2 mu x squared plus mu x squared, we get the second moment minus mu x squared, which is just the first moment squared. Okay, we're going to use this formula. And so all we need to do is find this one, the second moment, which is by definition 0 to infinity. Now this time instead of x, we have x squared. Okay, 1 over lambda e to the negative x over lambda dx. Okay, again, very similar to what we did in expectation, we're going to use integration by parts. This time we have this as our function that we're going to derive, and this as the function we're going to integrate, because remember this is a polynomial and this is an exponential. Okay, so what happens when we derive the polynomial? Then we'll get 2x, right? And what happens when we integrate the exponential? When we integrate the exponential, we get e to, okay, let's try doing it in our head if we can. When we derive this, we get negative 1 over lambda. So, okay. So this will work, okay. Because if we derive f, we see that using chain rule, we'll have negative 1 over lambda times e to the negative x over lambda. And so the negatives cancel, and we end up with f prime. And if you're wondering how to do this on your own, just comes with practice. I'm sure there's an easier way to explain it, but you can look up calculus videos on your own. Okay. So plugging it into our integration by parts, we have the integral of f prime g being equal to fg minus integral of fg prime. And therefore, we'll have x squared times negative e to the negative x over lambda from 0 to infinity minus the integral from 0 to infinity of fg prime. Okay, f is negative that, and then times 2x. Okay, let's cancel the negatives. Okay, and then using the same steps as above, we'll see that this side equals 0. Why? Let's first start with this one. Okay, if we plug in 0, then the 0 squared, it's just 0. And so it all multiplies out to be 0 because on this side we will have a -1. Okay, let me erase that because it's clear. And then if we plug in infinity, then we see we have x squared over e to the negative x. Oh, it becomes positive x over lambda. And as x approaches infinity, this approaches 0. We can use L'Hopital's rule, but let's just take it as a given because it's similar to having x over e to the x over lambda. Okay, so by the same reasoning above, the whole thing on the right, on the left is equal to 0. Okay, so all we need to care about is this thing. Again, we'll use integration by parts. Let's bring the 2 out into the front. Okay, and we have 2, 0 to infinity, e to the negative x over lambda, x dx. Okay, again, remember that this is easy to integrate. This is easy to derive. And so if we derive x, we get 1. If we integrate e to the negative x over lambda, we'll get e to the negative x over lambda, -1 over lambda. And remember, we have to do this one minus the integral of that one. I'm hurrying because it's the same steps again. So we have 2, and then we have -x over lambda, e to the negative x over lambda from 0 to infinity, minus the integral from 0 to infinity of this one, right? Okay. -1 over lambda, e to the negative x over lambda, dx. This was using integration by parts. Okay, and by using the same reasoning as above, and so I'm going to hurry through this time. We have 0 and infinity, and when we plug in both of them, we'll check that it's both 0, so it becomes 0 minus 0, and so this whole thing is 0. And all we need to care about is this side, but then I'm going to cancel the negatives, and I end up with 2, 0 to infinity, positive 1 over lambda, e to the negative x over lambda dx. When I integrate this, I end up with 2 e to the negative x over lambda. 1 over lambda stays the same, but then to cancel this when we derive it, we have to multiply by -1 over lambda, right? So when we use the chain rule on this thing, we'll get -1 over, oh, sorry, it'll, did I do something wrong? Did I do something wrong? Oh, it looks like I did something wrong here. So sorry, let me change this mistake real quick. When we derive, when we go from here to here, we're integrating. And so if we derive it this way, then we'll have -1 over lambda, and so it's actually negative lambda here. So let me correct my mistakes in yellow. It'll be negative lambda here, and negative lambda here, but then the negatives cancel, and so we get positive, and here, and here, and here. So many mistakes, lambda. And so the lambda stays. To cancel this one, when we derive, I have to multiply by negative lambda. Okay, this looks a lot better. So this is the integral. Okay, rewatch the video if you need to. And we're going from 0 to infinity. Okay, if we plug in infinity, now it's routine, we get 0. And if we plug in 0, we'll get negative lambda squared e to the 0. And so the negatives cancel, and so we get lambda squared times 1, which is just lambda squared. Okay, this was, oh, sorry, did I forget the 2? I forgot the 2. Okay, 2 lambda squared. Okay, and remember that this was expectation of x squared. And remember that variance is equal to the second moment, expectation x squared, which is what we just found, minus expectation of x squared. Okay, so we have 2 lambda squared for this guy, minus, remember, expectation x we found was lambda squared. Lambda, right? And it's being squared, so I squared it. And therefore, this is just lambda squared. This is the variance. So variance is lambda squared, expectation is